Hello, everyone. Thanks for tuning in. So this is a paper that we presented at SciTech 2024 that went over some controls work on a bio-inspired fighter aircraft. Um, so just a little bit of background on the vehicle. So this is the bio-inspired rotating empennage, and you can see the various control effectors highlighted in different colors. So there's the ailerons in blue, the stabilators in green, the rotating tail in purple, and then the throttle setting in red. Now, previous work has looked at studying the aerodynamics of this vehicle, as well as studying the dynamic stability, excuse me, as well as the structural design, how we would make this rotating tail on a pre-existing statically unstable fighter aircraft. And this work is just adding to that body of studies of of some preliminary control analysis on a linear controller to stabilize the aircraft due to some disturbance. Now there are a couple different models that we use to study this aircraft. The first that I'm going to go into a little bit more detail on is the nonlinear aerodynamic model. Now, traditional aircraft, we would look at, uh, for example, each of the forces and moments. We could look at each of the forces and moments in this way. So we'd have the effect of each of these states or aircraft parameters or control states on, for example, the yawing moment coefficient. And you can see each of these constant coefficients in this equation. But for the buyer, not only do we have more coefficients in this equation. We have coupling terms, etc. But each of these coefficients, you'll notice each has a little hat. And that hat is due to each of these coefficients being a function of the tail rotation angle. And so here's a plot from the work done by Bolander. You can see that dashed line, which is the baseline aircraft. So this baseline statically unstable fighter aircraft. And then you can see the change in the yawing moment coefficient C and beta as a function of this tail rotation angle. And so you can see this aerodynamic model is highly nonlinear. And because of that nonlinearity and a little bit more information that we'll get to in a moment, we're not able to attack this problem using traditional control design techniques. Um, Now, not only do we have nonlinear aero, we have nonlinear dynamics. We also have first order actuator dynamics. Um, and then we have a couple models that we use to implement disturbances and to build this control design for turbulence as well as aerodynamic model error. I'm not going to go into too much detail on those. For more information, you can check out the paper. So once we use these dynamics models, we can create a linearized system, and that is in the paper. You can check that out about some trim condition. In our case, we use steady level flight at 15,000 feet, Mach 0.6, and we get this control matrix shown here. Now, there's light coupling in this matrix due to the nonlinearities of the system that show up between longitudinal and lateral control and states, aircraft states. And this coupling only increases for larger Bayer angles. And so we wanted to pick a control methodology that would work whether we're flying at steady level flight or in, for example, a steady coordinated turn where that tail angle would be larger. Um, and so this light coupling, particularly here, which grows stronger in larger tail rotation angles, makes it so that we can't use traditional control techniques of dividing, for example, a longitudinal and a lateral controller or a roll, pitch, and yaw controller, etc., or going based off of dynamic modes. We have to create a multi-input, multi-output controller. Now this system is open loop unstable. It's unstable in the short period mode because it's a statically unstable fighter aircraft, and in the Dutch roll mode because we got rid of that tail, which provided the majority of the yaw stability. Now the control methodology that we're using has a few assumptions baked in. Once again, this is preliminary controls work. We wanted to look at basically if we can get anything to work, it will probably be this methodology. And if this methodology works, or maybe I should say, if this methodology doesn't work, then nothing else will probably work. So there's a few assumptions, limitations that we accepted that we know are not good, but we decided to go forward anyway to continue these analyses so that, once again, going back to that, if this works, then maybe it'll work, for example, if we don't do perfect full state feedback. I'm probably beating a dead horse. For more information, you can check out the paper. So the first was perfect full state feedback. We are assuming that we're getting perfect full state feedback that we can use to build this or to implement this control design. The second is that we have a continuous control, and that means, for example, no quantized control. We also assume there was no latency in the controller, and one perhaps limitation is that we dropped the actuator dynamics from the control design. Um, and for reasoning on that, you can check out the paper. There's just too much information there to bring up here in this presentation. We used a linear controller. We used LQR. Now, the purpose of LQR, or rather the goal of LQR, is to minimize the cost J as time goes to infinity of this cost function right here. So it's dependent on weightings on the state, that's the Q, and the weightings on the control, that's R. And this is done by solving for some positive definite matrix P in the algebraic Riccati equation, which we can use to develop a gain matrix K, which can be implemented in simulation like so. Now, we've talked a little bit about the control methodology. Let's talk a little bit about the control design. In other words, the actual weightings, et cetera, that we used. So we use these weightings on the state and the control. And if we use these weightings with the linearized system, we get these gains. And I'll talk a little bit to that. So just a couple of things that we found were interesting. The aileron control was primarily dependent on feedback of roll rate and yaw rate. The elevator control was primarily dependent on pitch rate, yaw rate, and elevation angle. The tail rotation angle, the Bayer angle, was primarily dependent on yaw rate. And the throttle setting was primarily dependent on feedback of the elevation angle. And so you can already see that it's very, very strongly dependent on feedback of this yaw rate. And we'll touch on that back in a moment. So there were a couple different ways that we used to evaluate this controller. The first was to look at the eigenvalues. Now that's kind of a hit or miss that we get all the eigenvalues in the left half plane. But we also took a look in the time domain. We ran simulations, Monte Carlo simulations using, firstly, initial condition dispersions. If we start the aircraft off at trim and perturb it in body fixed rotation rates, roll, pitch, and yaw, can we bring it back? Can we stabilize the aircraft back to that trim condition? We also took a look at implementing aerodynamic model error. For example, if we had 5 or 6 or 7% error in our lift coefficient or side force coefficient or something like that. And then lastly, we implemented turbulence. Now, this turbulence came from the von Karman gust model. We used the method originally developed by Beal. And for more information, you can check out the paper. And then in the frequency domain, we looked at the system using input sensitivity. Now, we did that because we had more states in our feedback design than we had inputs, and so anything else in the inputs on this multi-input, multi-output controller we couldn't really speak to. Okay, so here is a plot of the initial condition dispersion. We start off the aircraft off at trim, and then we turb it in rotation rates, and we bring it back to zero, and it's simulated for 15 seconds. Now, it's a little bit difficult to see, so I'm going to zoom in. But before I do, I just want to note that these blue lines, those are the limits on the control and actuator rates, or excuse on the inputs and the rates of the actuation rates. And then in this middle plot, there's gray lines and black lines. The black lines is what's being commanded by the controller, and the gray lines are the actuator states. So here's those same plots zoomed in for the first second. So you'll notice once again, or perhaps I just want to recall that we do stabilize the aircraft, but it does saturate in the actuation rate of elevator and the tail rotation angle, the Bayer angle. One other thing I want to note is that with these zoomed in, it's a little bit harder to see, but we hardly use the tail rotation angle, the Bayer angle, or the throttle setting. And we'll come back to that in a moment, but I want to draw attention to that. So then we took a look at estimating some region of attraction for dispersions in roll rate, pitch rate, and yaw rate. And that's what we have here from left to right. And convergence was determined as shown in this equation up here based on some matrix E, which was dependent on some maximum value in each of the aircraft states. And that's how we define convergence. And once again, can't go into too much detail there. For more information, you can check out the paper. But you can see that we simulate for 15 seconds. And the time to converge takes longer and longer. And once it gets up to 15 seconds, we define that as unconverged. So we use these plots to estimate a region of attraction, which has 1 sigma values in roll of 100 degrees per second in roll rate, 12 degrees per second in pitch rate, and 3 degrees per second in yaw rate. So then what we did was we took this defined region of attraction and we ran Monte Carlo simulations with no error, with and without error and turbulence, and evaluated the percent success. In other words, 1,000 cases each for 15 seconds. Within that, do we reach these convergence bounds within those 15 seconds? So the first is with no error, no turbulence, and we get within those bounds 98.7% of the time. And then if we add in turbulence, we get within those bounds 97.1% of the time. If we have error but no turbulence, um, we get there 97.1% success of the time. Now, once again, I want to reemphasize all of these simulations have initial condition dispersions. It's just dependent on whether or not we had error or turbulence. And you can see the axes of the initial condition dispersions on the plots. And lastly, 91.1% success with error and turbulence. So now I'm going to caveat these results. These may sound really good, but it's purely dependent on what convergence bounds we have defined. And so you can check out the paper for more information there. We also wanted to take a look at the frequency domain. Desirable sensitivity values are, we would want to have large singular values at low frequencies and small singular values at high frequencies. And so you can see this plot on the right that the aileron and elevator inputs are meeting this desirable sensitivity, but the throttle setting and the tail rotation angle not so much. Particularly the tail rotation angle, which starts off negative and then slowly, changes to decrease. And so I want to recall, back when we were looking at those simulations of initial condition dispersions, we showed that we didn't really use a whole lot the Bayer tail rotation angle or the throttle setting. And so that made us wonder what would happen if we neglected those from the control design. So these are those same numbers that we looked at before with those spinning plots. So if we have no with and without error and turbulence, these are the percent success, depending on that convergence bound. If we include Bayer and throttle in the controller design, and then if we drop Bayer, there's at most a 1% decrease in success. And then if we drop throttle, there's anywhere from 1% to a 10% drop in success, and that depends on whether or not there was error. And if we drop Bayer and throttle, there's anywhere from 1 to 15% success decrease, depending on whether or not we included, or whether or not there was error in the simulation. Now, these results were really interesting. They made us realize that at least at this specific trim condition for this control design, we can drop the tail rotation angle from the control design with minimal effect on the percent success. And not so much for the throttle setting. We can't drop the throttle setting without it affecting our performance significantly. We took a look at the same thing in the frequency domain. So you can see here the singular values for if we drop Bayer, if we drop throttle, and if we drop Bayer and throttle, and you can see the results there. That particularly the leftmost and the rightmost are more the plots that we'd be looking for. High We want to have high singular values at low frequencies and low singular values at high frequencies. So just a few closing remarks. So there were a couple things we learned from this work. The first was that the buyer can be stabilized using LQR at this trim condition, using the control design and assumptions that we've talked about. We also learned that the buyer can be stabilized without use of the rotating tail, once again at this trim condition with this control design. Now, further work will be looking at using a similar control design to develop a controller for an aircraft that is trimmed in a steady coordinated turn. So a larger tail rotation angle, would we be able to get away, for example, with dropping the tail rotation angle from the control design? As well as gain scheduling, looking at taking the aircraft from one state, from one airspeed and altitude, and bring it to a higher airspeed and a higher altitude. We'll also be taking a look at tracking control, working towards developing an RC subscale version of this vehicle that we would use test this control design on. And lastly, further work will look at nonlinear control and as well as perhaps dropping some of the assumptions that we used in this control design. Thank you for listening. This work was funded by the Air Force Research Lab. Um, Once again, thank you for listening. I appreciate your attention. And I'll have the link to the paper in the comments and look forward to seeing any comments on the video. Thank you.